So this is actually a redo of STA 13, where I'm actually going to rework through things a little bit more slowly than in the last attempt. So first we're going to be looking at the gradient of a complex vector. So this is a vector in 1 and 3 subspace, so a vector and a trivector. So it's a complex vector. When you take the gradient of a complex vector in general, you return to the even subalgebra of the spacetime algebra. And where we talked about that before was in or was in the STA 5 video. So here. So in STA 5, when you take the field gradients, you have that if you have a vector field, the vector field goes to 0 plus 2, and the trivector field goes to 2 plus 4. So a scalar and bivector, and a bivector and pseudoscalar term, which is summed up here. Or sorry, no, summed up here. And that's what we are going to be looking at for the complex vector potential. So if we have AE, AM in STA1, so they're vectors. So they're in STA1 such that Z is equal to AE plus AM I can write that better. I. Then you have the gradient of Z, and you can break up each component. So you have gradient of AE plus gradient of AM I, which is equal to the divergence of AE plus the curl of AE plus the divergence of AM plus the curl of AM right here. Which I will then write out like this in one final form. Basically copy this. Plus oh, and then this, I just realized this should be a wedge. So then recalling from the stuff I just showed, where you get different terms, this is going to be scalar, so this is going to be grade 0. This is going to be grade 2. This, because this component is grade 0, but then the pseudoscalar multiplies it, so it's grade 4. So this is grade 4. And similarly, this is grade 2, but it's times the pseudoscalar, and because bivectors are dual to themselves, you remain a grade 2. So this is also grade 2. And so if we want the gradient of this complex vector to only give a bivector, because remember, bivectors are what we need to describe electromagnetism. So we say this. We need the electromagnetic field to be a bivector. So if we want the gradient of z to be a bivector, so if we want the gradient of z to be a bivector field, then we must have that the grade 0 part and the grade 4 part are equal to 0. So we must have that the divergence of AE is equal to the divergence of AM, which is equal to 0. So it must be equal to 0, which this would allow F to be equal to the gradient of Z, which would then be equal to just the wedge of AE plus gradient wedge AMI. And this is what's called, this is something in physics that's known as the Lorentz gauge condition. In the Lorentz gauge condition, I think his name is Ludwig Lorentz, he realized that it was easier to solve Maxwell's equations if you assumed this to be true. So it was just a math technique. But here it's a result of the geometry of spacetime. The only way to make Z describe F is to have these components be equal to 0. So this is the Lorentz gauge condition. Now, what we must do is find a solution for Z. Let's find a solution for Z. And then I'll say this. Recall the form of F. So recall that F, when we solved for F, it was equal to SK, where this is this SK right here is the canonical bivector F. And we have E to the plus or minus K dot XI, where this K is the 4 vector of this is the wave 4 vector, and then this is the 4 vector of position. So we just need to recall this. Well, I must be of a similar form. So there's a thing in wave mechanics. So we can say in general, a wave looks like e to the, and then you have some constant I, which implies that the derivative, so like if you have let's just say that you take the derivative with respect to alpha, then, or if you take the derivative, let's rather say that this is like alpha beta. So if you take the derivative with respect to alpha, then you get beta e to the alpha beta I. then this emphasizes that the derivative gives a wave as well, but with an extra constant out front. And this didn't have to be derivative with respect to alpha. It could have been with respect to beta, and you get alpha down here. The point of this was to show that the derivative with respect to something in the exponential gives you still a wave, just with an added constant out front. Well, we know that we want to take the derivative of z to get to f. So we want to take the derivative of this to get we want to take the derivative of some constant times this wave to get this constant out front, so that we can get f from this. Well, what I should have done is actually bring this I down as well. You have a constant I out in front. So there's no I out front here. We know that this is scalar, and that if we were to take the derivative of this, we get an I out front. So if there's no I right now, then that must mean that it was there before the derivative of this was taken. That is, so then we can say, therefore, consider I and S, because S is out front, but we don't want K. So if we took the gradient of this X will disappear and we'll just have a factor of K, and K will come down. So we just consider this. If we consider that, then the gradient of IS E, I'm just going to copy this so I don't have to rewrite it every time. The gradient of this, well, I and S aren't going to change, so you can factor that out. Then taking the derivative, you get IS, or you get this I right here, and this K will come down. So you're going to have KI, IS, the exponential. This is going to be equal to negative Ks of the exponential, which is equal to Sk, the exponential. So just now we found that the gradient of this, the gradient of that is equal to f. So we can say that therefore z is equal to is e to the plus or minus k dot x I. So this is what's called a monochromatic solution, because there is one wave vector, which means, and recall that the wave vector describes a color or a frequency. And because there's only one present in this is called a monochromatic solution. So I'll say monochromatic solution. Monochromatic solution. So then let's look at polychromatic solutions. So polychromatic potentials. So we have the general form of F is equal to SK. So if we go back to polychromatic F, then the definition is that this one depends on different frequencies. Get this plus alpha minus. So we get this. This was the form that was given in, oh, let me see, which video was it? I think, yeah, it was in the polychromatic wave packet solution, so in STA 12, where this was the solution for F given, where you have multiple colors. So you're summing up over all the right-handed and all the left-handed solutions. Well, we have that, we know that SK is equal, or actually, no, we don't even need that. I don't even need to give that. So it's going to be the same thing here. We know that when we take the derivative with the gradient, so the derivative with respect to space, then it's only going to affect these, and it's going to do a similar thing here. So there's going to be no k in the vector potential, and there'll be an I, just an s. So that means that z is going to be is negative infinity, infinity, d omega. Oh wait, hang on, no, I do need to explain another part. So you can expand because if you recall, k is equal to omega over c k naught, where k naught is just the purely directional part, and you just take the magnitude of it out here. So that means that you can rewrite these exponentials up here and rewrite these with an omega over c, and then you just say k naught, omega over c. So we know this, and that'll be up here. And we also know that sk is equal to omega over c sk naught. And so for a similar reason, we're going to have, or for a similar reason for up here, except now we're differentiating and we're doing things explicitly with omega over c. There's going to be a factor of omega over c that's going to cancel out here. It's going to end up with I s. Then you get c over omega d omega alpha plus omega e plus or minus And then for some reason the book or the paper doesn't explain. It just says that the derivative of the minus component is going to give a minus sign. So you need this. It doesn't explain, but it just says that. So we have that. Okay. So now we're back and we're going to look at the other one. So where we get the potential from all the plane waves. Potential from all plane waves. Where we're following section 12. Where we're just going to be doing this. So I'm going to copy this so I don't have to rewrite it. Where we're just going to look at the adding all plane waves going in every possible wave vector direction. So this would be what the bivector looks like. And this implies that the vector, a complex vector potential, needs to be I negative infinity infinity d3k 1 over the magnitude of k s of k, and then just these. But again, there's a relative minus sign that the authors didn't really explain, except they're just like, it's there. So the derivative is minus, so that we get this. Yeah, so I don't know, there's not much to that, and there aren't many examples we can do with this. This is a pretty complicated equation. I can't solve this by hand. And I don't want to set up a computer program to solve it for us. So we're just gonna leave it at that. It's that. Then there's a little thing we need to remember. Remember alpha plus or minus holds a factor of k, of the magnitude of k. Now we're going to look at the relative frame. So we were using the complex vector z, but now we're going to break z into relative frames, where, again, relative frames are space-time splits. So relating things to their frame-dependent form. So relative frame of vector potential. So if we have the vector potential, or the complex vector potential, z equals ae plus ami, where both ae and am are vectors. Then when we break ae into its relative frame, we pull out a gamma to the left, we get phi e minus a. And for am, we pull out a gamma naught, we get phi m minus c. We can rewrite the Lorentz condition or recall the Lorentz condition, was that the divergence of these vectors are equal to 0. So if the divergence is equal to 0, so if the divergence of AE is equal to the divergence of AM, which is equal to 0, then the divergence of AE, expanding that out, we get partial naught phi E plus the gradient, or times the dot product divergence of A, which is equal to 0, because this is the scalar part of this vector equation. And likewise, let me move things to the left so I have room. Gradient of AM, or the dot product of AM, get this. So these are the more traditional Lorentz conditions. This is when you write the Lorentz conditions traditionally, this is what they'd look like. So we can apply this split, applying this split to F. So we can apply this to F, which is equal to the gradient of Z. So we can express F in terms of, or like in relative form. So we get F equal to the gradient of Z equal to partial naught gamma naught squared. So this is just expanding, out the gradient, and then expanding out the vector potential parts. So this is what that looks like. And then this is equal to naught Fe minus partial naught A minus gradient Ve plus plus I'm just going to copy this all and then change the lettering. Which then we know that this plus this is 0, this plus this is 0, so we can cancel those out. And then This right here, these i's cancel, and so we can put this on the other side. We can get minus curl of C. And we get a similar result on this side. And this curl of A comes from over here. There's an I, you can factor it out here. So if you break F into relative forms, then this means that the electric field is going to be given by this, and the magnetic field is given by this. So E is equal to this. And B is equal to this. And these should actually look similar to Maxwell's equations. And that's just because of the geometry of spacetime. That's just the way that these objects change.